Let's use all of the tools that we have now to completely factor a given polynomial. So if we look at this one here, it just might take us a few steps to get to our final answer. I have 6x cubed minus 96x. I think step one, whenever you're factoring a polynomial, is remove the greatest common factor. So looking at these two terms, I have a 6x cubed and a 96x. So I believe the most I can factor out in terms of a number is going to be 6 because that goes into 96. And I can take out x since that is the smaller of the two exponents. So this is my first step. Take my expression, write 6x, and figure out what is left over after removing it. So taking out a 6 and an x leaves me with x squared for the first term. And then I have minus 16 for the last term. And again, a good way to check this is by distributing back in. 6x times x squared is 6x cubed, and 6x times 16 gives me this negative 96x. So this portion is factored, and I'm left with x squared minus 16. And I'm noticing that that's a difference of two squares. That is, I have 6x, x squared's already set up as a perfect square, but 16 is 4 squared. We can now use that whole a is equal to simply x and b is equal to 4 to use our difference of two squares formula. The 6x does not change, but you can write the next two pieces as a plus b, which is x plus 4, and a minus b, which is x minus 4. I know when a polynomial is completely factored when 6x can't be broken apart, x plus 4 and x minus 4 can't either. We've taken it as far as we can go, and we've completely factored this expression. So now let's try this idea in this polynomial that has 3 terms. All right. Okay, I think we'll have to start with the greatest common factor again, because there's definitely some number of x's that can be removed from each piece, and that's going to be x cubed. And the number I could take out from every term at most could be 3. So if I look at 168 and divide that by 3, I get 56. So okay, I can remove 3 from every term, but why not remove the negative as well? So I'll put negative 3x cubed, and that's going to change the sign on everything that remains. So if I take out negative 3 and an x cubed, we're left with x squared, then we get minus, we have x to the first power, and then another minus 56, and that's just by itself. So you don't have to take out the negative, but if we have to factor this x squared minus x minus 56, having a negative here could be confusing, so I just took that out as well, and I changed the sign on every single term that appears over here. So to completely factor this polynomial, I now have to deal with the x squared minus x minus 56. I think I'm going to use a guess and check approach to factor this trinomial. So I can't do anything with the negative 3x cubed, but maybe I could guess the factors for the second part. You'd have to have an x and an x, as well as a positive and a negative. The x times the x takes me to the x squared. The positive and negative would multiply to a negative number. I need two numbers that multiply to a negative 56, yet add to a positive 1. And the two numbers that are going to do that are negative 8 and positive 7. If you add those two, you get negative 1. The product is negative 56. I put 7 here. I put 8 here. So that was a positive 7 and a negative 8. Clearly, this is going to multiply back to x squared minus x minus 56. I look at each term that I have, and I see that I can't factor anything else any further, so this is the final answer. All right, so just a couple more examples of completely factoring a polynomial. Here I have 100x to the 10th plus 1600x to the 8th. Okay, again, we're having to deal with this greatest common factor of I can take out 100 from both terms and also an x to the power of 8. That would leave me with a 100x to the 8th outside of the parentheses, and within the parentheses I have x squared plus 16. And here we have, well, this is a sum of two squares. This is not a difference of two squares. So we don't actually have a formula for this expression. In fact, we cannot factor this any further. So this is a sum of two squares, which means we're stuck. Even though there is an x squared, and sometimes x squareds can be broken up into two separate pieces, the fact that this is a positive instead of a negative means there's no way that we can break this apart using real numbers. So that's actually it for this problem. We have completely factored this polynomial because this piece can't go any further. So let's see if something like that happens in the last example. All right, so this is a trinomial. Definitely some greatest common factor can be removed. If I focus on the numbers, you can take out x squared from everything. That's the most you can take out in terms of the x's. And okay, I'm noticing that 7 goes into 42 and 35. Does that go into 119? And it does. Okay, great. So that means the most I can take out is a 7 from all three terms. All right, so the next step would be to write down the 7x squared, and then what is left over? So from 42, I get 6x squared. From the 19x cubed, I get plus 17x. And then for my last term, it's plus 5. And again, you can check by multiplying this back in just to make sure it takes you to this previous step. I've dealt with the 7x squared, but I've not dealt with this. You could use a guess and check approach. I mean, if that works, there's absolutely nothing wrong with doing that. Guessing could be tough here because of this 6. It's not just a 1. So what I'm going to do is use, I think, a factor by grouping approach. You don't have to do this, but I'm definitely going to, where what we'll do is take the 6 and the 5 and multiply those two things together, which gives me 30. Then I want to find two factors of 30 that when I add them, it takes me to 17. Okay, well, actually that's not too hard to guess. That's a 2 and a 15. The product of 2 and 15 is 30, the sum is 17. I'm going to use these numbers to factor apart this trinomial. What I'm going to do is take 17x, break it apart into a 2x and a 15x, and use a factor by grouping approach on those four terms. Let's write that out. So there'll be a little bit of work here, but I have 7x squared. I'll copy down the 6x squared, and instead of 17x, I'm going to write it as 2x and 15x. And where that is coming from is these two numbers here. I just put an x after the 2 and the 15 and replaced 17 with this sum. I broke this apart. The last thing to do is copy down the plus 5. And I'll note that clearly this expression and this one are equivalent, because if I add those two, it takes me back to 17. All right, so what I do now is factor out the greatest common factor from the first two and the last two terms separately. Let's see what that gives us. We get 7x squared. I'm going to have to incorporate some extra parentheses, but we'll get rid of them at the very end. If I look at the first two terms, the greatest common factor is a 2x. So for just the first two terms, that leaves me with a 3x and a 1. All right, now I'm going to do the same thing for the last two terms. The greatest common factor is a 5, which would, and this is important, it leaves me with a 3x and a 1. For this process to work, this and this have to be identical once you go from this step to this step, because now you can factor out 3x plus 1 from the first and last terms. So I'm going to take this out and write it here. I get 7x squared. I remove the 3x plus 1 from both terms, and that leaves me with 2x and 5. And as I noted, I have this extra set of parentheses, which is redundant. You can leave it, but I'm going to get rid of it because it is unnecessary. I just have 3x plus 1 and then 2x plus 5, and this is my final answer.